In this video installment, we will be talking about a little bit about bonding in general, but more specifically today about ionic bonding. We will be learning about different types of bonding in future videos. Atoms bond because many atoms, except for the noble gases, aren't necessarily the most stable with the number of electrons they have. And they can become more stable by either losing, gaining, or sharing electrons with other atoms, oftentimes to give themselves a full set. In fact, the octet rule, octet meaning 8, means that many atoms will gain or lose electrons to have 8 valence or outside electrons, and that is how they will be most stable in nature. The octet, again, says they tend to do this. They do not have to always follow this octet rule. We will be focusing on ionic bonding, which is where atoms gain or lose electrons to become stable. So I have pictured here 4 example atoms: sodium, calcium, iodine, and oxygen. For sodium to get into, so we're going to pull sodium out first. For sodium to become more stable and fulfill the octet rule, it can lose 1 electron. So it has 1 electron in the 3rd energy level that is not held onto very strongly, so that 1 electron can easily go. This leaves sodium in the state of becoming a sodium plus ion, which would be written as Na plus. And then this 1 electron needs some place to go. So if we take another atom, say for example iodine here, iodine, if you count out what's left, it is very outside energy level. We have 1, 2, 3, 4, 5, 6, 7 electrons, so just 1 short of that 8. So if the electron from the sodium goes over to the iodine, and I can't actually put it on because it will go underneath, the iodine will have gained an extra negative, and so now instead of being iodine, it is an iodide ion, or an I minus. Now these 2 atoms, the sodium plus with a positive charge and the iodine minus, are attracted to each other, since positives and negatives attract, and can form a compound, which would be sodium iodide. We'll get into all that in a little bit later. Okay, if we look at calcium, a calcium atom has 2 electrons and it's very outside energy level, out in the 4th energy level. And if you take something like oxygen, which has 6, both of those could go over to oxygen, making a compound. Or you could take 2 different iodines. Oops, I guess I gotta duplicate that. And then 1 electron from the calcium could go there, and 1 electron could go there. So I make a calcium 2 plus ion and 2 iodide I minus ions. Now you can see that working with these shell models of the atoms with all their electrons drawn out is very cumbersome. It's actually also very unnecessary, because for the most part, only the outside electrons are going to participate. You can see these inside electrons don't really do anything. So what chemists do is they use something called Lewis dot diagrams, which show only the valence or the outside electrons. So if we look at lithium, lithium being 1s2, 2s1, has just 1 outside electron. Nitrogen being 1s2, 2s2, 2p3, the 2nd energy level is the outside energy level. You add up both the 2 and the 3. There are a total of 5, 2, 3, 4, 5 outside electrons in nitrogen. So when we do this, we can see that lithium with only 1 electron, the tendency for lithium would be to lose that 1 electron. And if it lost the 1 electron, it would become 1 plus. Nitrogen, having 5 electrons to begin with, to get its 8, would have a tendency to gain 3 additional electrons. So we'll put in the 3 new electrons to get its 8. So nitrogen would have a tendency to become 3 minus with the additional 3 electrons. When you look at the periodic table, because hydrogen's column has 1 valence electron, when you're drawing its Lewis dot structure, you would give 1 dot to anything in hydrogen's column. For beryllium's column, because they're all 2s2s, this column would get 2 dots for 2 outside electrons. Boron's column gets 3 dots. Carbon's column gets 4 dots. Nitrogen's column, 5. Oxygen's column gets 6. Getting kind of messy there. Fluorine's column gets 7. And then 8 will go into the noble metal, or the noble gases. If we look at what charges are more likely to form, we can follow the periodic table here. Because the first column is likely, it just has 1 electron, it's likely to lose it and form 1 plus. The second column has with 2 electrons is likely to lose those 2 and become 2 plus. The boron's column is likely to lose 3 electrons to become 3 plus. Nitrogen's column is likely to gain 3 to become 3 minus. Oxygen's column or group or family is likely to gain 2 to become 2 minus. And fluorine's column is likely to gain 1 to become 1 minus. Once we know the charge of compounds, or of ions rather, sorry, we can figure out what compounds they will make by looking at the charges. You can think of ions as being like puzzle pieces. A sodium ion with 1 plus is like a puzzle piece that has 1 knob sticking out of it. A fluorine is like a puzzle piece that has 1 hole. So if I want to look at what compound would they make, it would make a compound that has 1 sodium and 1 fluorine, or NaF. That you always need to have the same number of positives as minuses in a compound. You can't have more of one or the other. Okay, so in a compound like NaF, that's pretty easy, just 1 of each. If I have a compound that has, or an ion that has 2 positives, like calcium does, and I want to make a compound with fluorine, I will need not just 1 fluorine, because that doesn't complete my puzzle. I will need to have 2 fluorines to complete my puzzle. So the compound made would be CaF2, named calcium fluoride. Let's say I want to make a compound out of something like Ca, calcium, and phosphorus. Here I don't complete the puzzle. A lot of people get frustrated with this and say, well, that's never going to work. If I take another calcium, that doesn't match up either. I need another minus to go with this plus. So I take another phosphorus. That still doesn't work. But wait, I have 2 minuses, so I have room for just 2 more pluses. And so the compound between calcium and phosphorus would be Ca3P2. I would write it out like this. I'll do my best with my finger here on the touchpad. Ca3P for phosphorus 2. Okay, and so this is how we write compounds. The subscripts tell us how many of the atom that comes before. So there are 3 calciums and 2 phosphoruses. These next couple slides I'm not going to really talk about. You'll get them in the notes you can print off, or take a look at the notes and you can read them just as well as I can read them to you, and kind of running low on time for this video here. So just make sure you take a look at these 3 slides about the different types of ions. What I want to go through now is how to go back and forth between the name of a compound and its formula. So as a chemistry student, this is very important for you to be able to do. When you have the name of a compound And you might want to go and look through those notes that I kind of skipped through really quickly before doing this along with the video to make sure read through them so you know what's going on. When you have a name like sodium chloride, the first thing you need to do is decide what ions it's made out of. Sodium, going to the periodic table, is likely to be a Na plus ion, and chlorine is a Cl minus ion. I look at how would they fit together. Well, if they're 1 plus, 1 minus, I just need one of each. So the formula would be NaCl. When I'm given a formula like this, Ca3P2, and I want to figure out what is the name, I do the same, I do kind of like the opposite. I always go and figure out what ions is it made out of first. So Ca, if I look up on the periodic table, is calcium, and it has makes a 2 plus ion. P, phosphorus, makes a 3 minus ion. The name of the 2 plus ion would just be calcium. The name of the P3 minus ion would be phosphide. So this would be named calcium phosphide. Tin 4 oxide. The 4 goes with the tin, and it tells us what the charge of the tin is. More correctly, it tells us the oxidation number, but we will get into oxidation numbers much later in the year. So for right now, we can think that is the charge. So tin 4 is the charge. Oxide is O2 minus if you look up on the periodic table. And so we find out you're going to use SN4 plus for tin, and then O2 minus for oxide. If I'm going to put these together, because this has 4 plus and the oxygen only has 2 minus, I need 2 oxygens to make this work. If you want to draw out puzzle pieces, you'll see that. Okay, and so I end up with SnO2 because I needed 2 oxygens for the one tin. With the name magnesium nitrate, again, I can go to the periodic table. Magnesium is there, and I'll find that it's a 2 plus charge. Nitrate is a polyatomic ion, and I will be giving you sheets in class to look up common polyatomic ions. Nitrate is NO3 minus, okay? And so again, the 3 does not go with the minus. The 3 being a subscript goes with the oxygens, so there's only 1 minus on the nitrate. So I need to have 2 nitrates to make up for magnesium. So what I do is I put the nitrate in parentheses so that I have 2 of this entire thing, which gives me 2 minuses that I need to go along with magnesium. Looking at Fe2SO43, on my ion sheet, it would tell me that SO4 is 2 minus. 2 minus times 3 gives me a total of 6 minuses here. So I need to have a total of 6 pluses, which means the iron is 3 plus. And then the iron 3 plus would be called iron Roman numeral 3. And then SO4 2 minus is called sulfate. Okay, I know this is probably a lot to take in on the videos. We have these examples here, and I encourage you to kind of work along, with these. We'll be working some more in class to kind of solidify this for you before giving you time to work on the worksheet by yourself.